Hello, today we are going to be introducing you to torque. So what is torque? It is the ability of a force to cause an object to rotate about an axis, or in fewer words, a force that causes rotation. This force has to act perpendicularly to an object in order to cause a rotation. So let's think about that, for example, by thinking about how you open a door. If my arm is this door, here are the hinges at my elbow. I have to push perpendicular to the door in order to open it. If I try pushing parallel to the door, if I try pushing in towards the hinges, that's not going to move or open the door. You have to push perpendicular in order to open it or to cause a rotation. How does an object rotate? It rotates around a spot called a fulcrum. So on my door arm example, I said the hinges were at my elbow. That is the fulcrum. That is what we are rotating around. My arm moves around my elbow, or the door moves around the hinges. That spot is the fulcrum. So take a second. Can you identify the fulcrum for each of these objects? On the teeter-totter, it is the point right in the middle that is holding it all up. And for a wrench, if you think about how you hold or use a wrench, there would typically be a bolt or something right at the center that you are trying to rotate around. So the fulcrum would be up here at the top of this wrench. Take a second to look at these examples and think about it. Pause the video if you need to, chat with a friend or someone who's nearby. Look at these four situations and see if you can identify the force, figure out if the force is parallel or perpendicular to the object it is acting on, and if it is causing a torque. So pause the video now, chat with a friend, and look at these four situations. On each of these situations, there is a force, so let's go through them one by one. In the first one, I am pushing a child on the back as they swing. The force is the push from my hand on the child, and it is perpendicular. The child's back and my force are perpendicular to each other, and it does cause a torque as the child rotates about the axis of the swing. Second, a child's weight is acting downward on the face of a seesaw. The force is the child's weight, and it is perpendicular to the seat of the seesaw, and that would cause a torque as the seesaw would rotate about its fulcrum. Third, we have pulling down on a wrench as you try to unscrew a bolt. The force is my pull down, and it does act perpendicular to the wrench, so it would cause a torque as the wrench rotates around the bolt. And fourth, we've got wiping dust off of the face of your TV screen with the palm of your hand. The force is my hand pushing into the TV screen, and that is parallel to the TV. So that does not cause a torque, and the TV is not rotating here. So how can I apply this? What is the math behind it? Here is our torque equation. Torque, we use this Greek letter tau to represent. So it's like T with a little curl on the end is tau. Torque is equal to force times distance. This R is the perpendicular distance between my force and the axis of rotation. It's measured in meters and is sometimes called the moment arm. So we've got a force in Newton times a distance in meters. Torque is measured in Newton meters. How can I tell if this is positive or negative, and which way does it rotate? Torque will cause an object to rotate either clockwise or counterclockwise. And counterclockwise is a positive torque, which means clockwise, going in the same direction as the hour hands on a clock, is a negative torque. You can think about this using an unofficial right hand rule. If I hold my right hand out, it feels more natural to curl my fingers counterclockwise, so that is positive. If I have to turn my fingers clockwise, then my hand is upside down, or maybe I'm just at an awkward angle. It's unnatural, so that is negative. So counterclockwise is positive. So let's look at an example question. Here I've got two children sitting on a teeter-totter as shown in this picture. It is supported directly in the middle by a fulcrum. How far from the fulcrum should this 45-kilogram child sit in order to balance the seesaw? So I have a 30-kilogram child sitting 3 meters away from the fulcrum, and I want to figure out where to put this 45-kilogram child so that the seesaw is balanced. It is not rotating. In order for something to stay balanced or not rotate, I need the net torque, or the sum of my torques, to equal 0. This is a state or a condition called static equilibrium, where I have things that are not rotating. Remember static friction, you were not yet moving. Static equilibrium, everything is equal and not rotating. So in this example, I need the torque caused by the 45-kilogram child to be equal and opposite to the torque caused by the 35-kilogram child. So let's look again at the picture to see, okay, I've got my 35-kilogram child sitting 3 meters away, 45 kilograms sitting X, or an unknown number of meters away. And I want these two torques to cancel each other out. So the 30-kilogram child will cause a counterclockwise rotation, or a positive torque, and the 45-kilogram child will cause a clockwise rotation, which is a negative torque. I want the sum of all of my torques, or my net torque, to equal 0. That is, my positive plus my negative should equal 0. If I rearrange this equation, I get that the torque caused by the 30-kilogram child is equal to the torque caused by the 45-kilogram child. Here I'm using 35 and 45 as subscripts just so I can keep track of which side of the equation is which child. So I have the force caused by the 30-kilogram child times the distance of the 30-kilogram child from the fulcrum is equal to the force of the 45-kilogram child times the distance of the 45-kilogram child from the fulcrum. So remember, torque is force times distance. Here, the force is the force of gravity on each of these children. So I have the mass of the 30-kilogram times acceleration due to gravity. Weight is mass times acceleration due to gravity, times the distance is equal to mass times gravity times the distance. Here I've replaced r sub 45 with an x because that's what I'm trying to solve for. That is my unknown. Plug in the numbers that I know. 30 is the mass. 9.8 is my acceleration due to gravity, which will give me the weight, or the force, of this child. The distance was 3 meters from the fulcrum. On the other side, I've got the force, or the mass times gravity, is 45 times 9.8, and I don't know the distance yet. Multiply to get 882 is equal to 441 times x, or my distance. Divide both sides by 441, and I get that the 45-kilogram child must sit 2 meters away from the fulcrum in order for this seesaw to be balanced. So the 30-kilogram child is 3 meters away, and the 45-kilogram child is 2 meters, is a little bit closer. That's the kind of problem that you'll be seeing with torque, mostly dealing with wanting things to be in static equilibrium, or figuring out what torque must be applied in order to counter something. If you've got any questions, let me or your teacher know. Bye!